So, Riley, why don't we notice special relativity in our ordinary lives? Look at the time dilation equation. So the time dilation equation says T equals T0 all over the square root of 1 minus V over C all squared. Write that down. Again, do you need to memorize it, Ethan? No, it's on your green sheet. But what I'd like you to do is I'd like you to circle this bottom section here. We call this bottom section the square root of 1 minus V over C all squared, the Lorentz factor. And it's actually because before Einstein published his paper, a mathematician whose last name was Lorentz said, look, I can't explain why this works, but I've noticed if I multiply things or divide things by this, I get the answer that we're looking for. Don't know why, but it works. So we've named that factor after him. It's often symbolized with a Greek letter gamma. Greek letter gamma sort of looks like a skinny fish doing a headstand. So the Lorentz factor, the gamma factor, is the square root of 1 minus V over C all squared. And this gives us a nice abbrev. From now on, I'll probably write this equation as T equals T0 over that. And I'll probably write T0 equals T times that, because it's a lot less writing, and it's a handy abbrev. Did I give you that on the green sheet? My brain says I think I meant to. Can you actually look and confirm for me is sort of what I was getting at there?
You did,
yeah. Okay. See what it looks like? Okay. It's this Lorentz factor that determines how much time dilates. So, oh yeah, here's where I said we can write the time dilation equation much more simply as T equals T0 over the little gamma thing. So, how much will 1 hour of time dilate for each of the following situations? Now, I didn't give you the speeds in percentages, so we are going to have to type in our C value of 3 times 10 to the 8th, and we're going to be constantly using this. T equals T0 all over the square root of 1 minus V over C all squared. Can you get your calculators out, please? And I'd like you to follow along with me. We're going to calculate the time dilation factor. We're going to let T0 equal 1. And we're going to see what's going on here. So if I type in 2 meters per second, I would do what's inside the bracket first. So I would go 2 divided by 3 times 10 to the 8th, V over C. Hit equals squared 1 minus that problem. On this line, my calculator gave me an answer of 1. Is the answer 1? I don't think so. It should be whatever 1 minus 4.4 is repeating times 10 to the negative 17 is, but it's so small that my calculator doesn't even acknowledge it as an answer. Then you typed it wrong. Okay? So again, ready? 2 divided by 3, make sure you use your scientific notation button. 8 squared, you will get 4.44 times 10 to the negative 17. 1 minus that. This is where my calculator kicks out. Others might not. Yeah.
When I do the 2 divided by 3 times 78,
yeah.
I get 0.0000.
So it's giving you this number written out. So it would give you 8 zeros. And then this 6, what's right next to this 6? It's just rounding up. Point being, when I said time was moving slower for Aiden as he was walking outside of the... True, But when I try and calculate it, I get a time dilation factor basically of 1. It's negligible. You're not going to lengthen your lifespan by walking more due to relativity. You'll lengthen your lifespan because you're exercising. Race car. Let's try a race car driver. So that's going to be 70 divided by 3 scientific notation button 8 equals squared 1 minus that. Oh, my calculator stops tracking the difference at this stage and says, for Pete's sakes, the answer is so close to 1, it's negligible. So even a race car driver really isn't going to notice much of a time dilation factor. Ooh, the fastest jet we ever created is the SR-71. It can go 1,000 meters per second, a kilometer a second. Maybe they're experiencing time differences. So 1,000 divided by 3 scientific notation button 8 squared 1 minus that. Oh. No, it's there, but it's so many decimal places down that I would need a special calculator to track it. If you do a Google search for a long number calculator, you can find online ones that will give you these answers. You can try this. But the point is, it's negligible. It exists, but meh. No. Yeah. Hey, the Earth moves around the sun, which means if the sun is at rest, is time moving slower for us than it is on the sun? No, we're the ones moving. We're the spaceship. The sun is the one at rest. Let's try that speed. So 29,600 divided by 3 scientific notation 8 squared. Ooh. What? Are we getting something? 1 minus answer button? Square root of that, right? And then 1 divided by that answer. For every second that passes by for us, how many seconds pass by for the sun? 1, 2, 3, 4, 5, 6, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros, and a 5. But it's there. Hey, the Earth is moving through the galaxy around the black hole Sagittarius A that's at the center of our galaxy. Is time moving slower for us than it is at Sagittarius A? Let's find out. So now let's go 2.1 scientific notation button 5th divided by 3 scientific notation button 8. Stretch your hand up. Yep. Okay, then this is important. I need to make sure you're typing this in right. Pause. Let's see, I'd done 2.1 times 10 to the 5th divided by 3 times 10 to the 8th, and then I square that. 1 minus that. Square root of that. 1 divided by that answer. You get 6 zeros and then a 2, 4, 5? 1, 2, 3, 4, 5, 6 zeros. Still not very noticeable. Really still negligible. UBC has a particle accelerator called Triumph, and there they get protons moving at 2.24 times 10 to the 8th meters per second. So, what's the time dilation factor here? 2.24 scientific notation button 8 divided by 3 scientific notation button 8 squared 1 minus answer button square root of answer button 1 divided by, for every second that the protons experience, how many seconds do the researchers experience? 1.5. And they have to take that into account when they're calculating half-lives and decay rates. If they don't, none of the numbers will actually work. They have to factor in the time dilation in their particle accelerator. Otherwise, they get nonsense numbers. So for every second that the proton experiences, the researchers experience 1.5 seconds. In other words, if you know that the proton event is supposed to take, let's say, 1 second, you will measure it as 1.5 seconds, and you will say that's the correct event. CERN is the Large Hadron Collider. They get muons up to 2.996 times 10 to the 8th. Divided by 3 times 10 to the 8th. Squared. 1 minus that. Square root of that. 1 divided by answer button. For every second that these muons experience, how many seconds do the researchers experience? 19.4 seconds. Stanford University has a linear accelerator. It's called the Stanford Linear Accelerator, or the SLAC. They get electrons there up to 2.9979 times 10 to the 8th meters per second. Divided by 3 times 10 to the 8th, the speed of light. Now what? Squared. Now what? Then you made a typo. Don't clear your calculator. I'll come look at it. 1 minus that. Square root of that. 1 divided by that. Okay, don't clear. If you get an error, don't clear your calculator. Don't hit clear. I'll come find it. So for them, 26.7 seconds for every second that the electrons experience. Pick your pencils up. Let's keep going. Einstein predicted not only does weird stuff happen with time, weird stuff happens with lengths. We have something that we call length contraction. Einstein's special theory of relativity makes other predictions about objects moving at speeds greater than 0. This one, I'm not going to do a mathematical proof, but he proved this. The length of an object will be measured to be shorter when it's moving than when it's at rest. This shortening is only seen in the direction of its motion. What? Turn the page. If the length of an object when it's standing still is L0, the theory of relativity predicts that the object's length when it's moving will be that. Hey, what's inside that square root? 1 minus. So this is often sometimes written as L equals L0 times gamma function. We've all turned the page, Aiden. There you go. Figured you'd figure it out eventually. So T0 was time on board the spaceship. T was back on Earth. L0 is the original length at rest. If you're at rest, what's your speed as a number exactly? So L0 is the original length at speed 0, whichever one of those helps you remember. And L is the, what we call, relativistic length. This is the one that changes depending on how fast you're traveling. What? So here's our thought experiment, example 1. I'd like you to imagine that we had a meter stick come racing past us at 99.5% of the speed of light. Pause. I like example one. I like example one. Example one is a nice question. What's this question asking me to find? It says, how long would a meter stick appear to be if it was moving past you with a speed of 99.5% of the speed of light? It's asking us to find an L. Is it asking us to find L, relativistic length, or L0, the original length at rest? So then, what's L0, the original length at rest? Please tell me you know this. Thank you. It's a meter stick. The speed it's traveling is 0.995 c. So the relativistic length is going to be L0 times that square root thingy. It's going to be 1 times the square root of 1 minus 0.995 c over c all squared. Annika, do you see? Do you see? Do you see? What do you see? What do you get? And you'll notice I'm leading you in your calculators a bit less because I'm seeing if you figured out how to type these in for yourself. Hint, you're going to get an answer less than 1. In fact, I'm going from memory and I'm doing some rough math in my head. I think you get an answer really close to 0.1. Do you not?
Yeah.
No, not 0.01. 0.1. There's no way you're getting 0.01. There's no way it's a centimeter long. 1 minus 0.995 squared. I took a shortcut. Square root of that. Do I need to multiply by 1? Well, will multiplying by 1 change anything, Owen? Okay. So, George, I get this. 0.0998, and if I round off to there, 0.1 meters. Yes? So, look up. As this meter stick went flashing by, you would not see it this long. You would see it that long. There's 10 centimeters. There's 0.1 of a meter. You would see the lengths compressed in this direction, but none of the lengths would be compressed in this direction. So all the numbers would appear really stretched and skinny. They'd have the same height, but they'd be really, 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 really thin. And if you did an experiment in your universe that required you to use this meter stick, your experiment, anything that you did, would measure this as being a 10 centimeter long meter stick. You would not be able to do an experiment in your universe to show that this was 1 meter long. It would behave like a 10 meter long, like a 10 centimeter long, 0.1 meter long meter stick. So you ready? That means while it was moving at 99.5% of the speed of light, in your universe, you could fit it inside a tunnel this big and it would completely vanish. Okay. Mr. Dewick, wait a minute. What about the meter stick itself? It's a meter long. How can it fit inside a 25 centimeter long tunnel and completely vanish? Good question. It gets weirder, but cooler. No. Because space-time itself is curving, and so that meter stick will not experience a 25 centimeter long tunnel. That meter stick will experience something totally different. It's all relative. In your universe, relative to you, you will see a short meter stick that fits inside a 25 centimeter tunnel. Totally works in your universe, but that's relative to you. If you were riding on that meter stick as a little miniature astronaut, you would not see a 25 centimeter long tunnel. You would see something totally different. Oh, it gets weirder. No, it's not. Sadly, it's not that simple. You would not see a larger tunnel. You would see events happening at different times that for your universe happen at the same time. In the meter stick's universe, they wouldn't happen at the same time. Time is relative. Time is relative. I like example 2. I like example 2. Example 2 is a nice question. An 85-meter long spaceship passes you. Now that 85, that's at rest. How long does a spaceship look to you? What's this question asking me to find?
L.
L or L0? Yep. L. Well, this is the at rest. So if I give you a length and don't tell you that it's moving, assume we're at rest. So it's going to be L equals L0 times the gamma function. I'm getting a bit sloppy. I didn't do the full DFIC approach because we just said out loud they're asking me to find L. So what's that 85? That must be the original length at rest. Square root of, oh, this time, will I see? No, the C won't cancel. I'll have to put a 3 times 10 to the 8th in the bottom of the fraction. So it's going to be 2.23 times 10 to the 8th all over 3 times 10 to the 8th. Don't forget the squared. Okay, this one's a little yucky. I'd probably start inside the brackets. 2.23 scientific notation button 8 divided by 3 scientific notation button 8 equals. Then I think I'd go squared. 1 minus that. Square root of that times 85. So at rest, the spaceship is 85 meters long, but when it went whizzing past you, you would measure this spaceship to be kind of really short and stubby. It would have the same width because none of the lengths will contract in this direction because it's not moving relative to you in this direction. But it would be kind of like you kind of warped a graphic. If you've ever taken a photo or a graphic and just pulled in one side to compress everything, that's what it would look like to you. Now, does that mean the people on the spaceship would notice everything warped? No. Relative to them, they will be noticing an 85-meter long spaceship. In fact, are you ready? As far as they're concerned, they are at rest. You're the ones moving. So they will see you all squished up very, very thin with the same heights as you go whizzing past. Both are completely correct because it's all relative. It all depends on your frame of reference. Suppose a spaceship is 100 meters long when stationary. You know what? I'm pretty sure that's L0 at rest, the original length. When it moves past an observer, the observer measures the spaceship to be 25 meters long. I think that's L. Prebner, what's this question want me to find? Did I give you a V equation on your green sheet that has L's in it? I hope I did.
Yeah. No. Yeah. Yes.
Read me that one. It's L over L0? Or is it L0 over L? Okay, that's the only part I can't remember because it changes depending on the situation. Okay. We're going to do the answer as a percent. And then we're going to do the answer in meters per second. On your test, I'll give you one question where I ask for the speed as a percentage of the speed of light, and I'll give you another question where I say, tell me in meters per second. So you need to know how to do both. So how are we going to do that? It's going to be, we're going to leave the C as a C temporarily. 1 minus L 25 over 100 squared. (25 divided by 100 squared). 1 minus that. Square root of that. And I get 0.96824583666 blah, 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 blah. I'll probably go to like 4 sig figs, 0.9682. So 96.82% of C. right? 0.9682 times c. That would be as a percentage. How can I convert this to meters per second? Instead of c, put what number there? Speed of light. In meters per second. How about 2.9047 times 10 to the 1, 2, 3, 4, 5, 6, 8? If you ever get an answer bigger than the speed of light, you've screwed up. Can't go faster than light in a vacuum. Sorry? If we allow you to take the square root of a negative number, you get what are called complex numbers. If we allow that, Einstein's equations predict a hypothetical particle called a tachyon. A tachyon is a purely hypothetical particle. It would travel only faster than light, but it would then also, we think, travel backwards through time. It would experience time in reverse. And I should say, we can't think of an experiment to prove or disprove that. So I could have equally just said to you, there's leprechauns and unicorns that go faster than light, and that would be equally scientifically valid, because there's no way to do an experiment to prove or disprove that either. Could be. I just think it's unlikely. I like example 4. I like example 4. Example 4 is a nice question. A certain star is 15.6 light years away. We did one like this. This is the Proxima Centauri question, where I said to you in the last lesson, we can't measure distances. Here's why. So how long would it take a spaceship traveling at 95% of the speed of light to reach the star A, as measured by the stationary observers on the Earth? Hey, the fact that I'm giving you this question in back-to-back lessons, and I've said I like this question, I like this question, I like this question, probably a hint. So, underline the word stationary observers. This wants us to find t. And because we're not moving yet, we're just going to use d equals vt. Part A is not relativistic yet. This is standard Newtonian physics. Deegan, you told me this earlier. How would I get the t by itself? On the Earth is going to be the distance that we measure from the Earth divided by how fast the spaceship is traveling relative to us. What distance do we measure? 15.6 light years. How fast is the spaceship traveling? 0.95 times the speed of light. Kiana, do you see? Do you see? Do you see? What do you see? So as far as we're concerned, home here on the Earth, this will take 16.4 years for them to get there. If you want to be more accurate, then I would also say double that, because that's how long it will take them to come back. And let's add 1 year for them to explore. We would say, okay, we're expecting them back 33.8 years from now. But for now, let's go with the 16.42. So let me bring that back. 15.6 divided by 0.95. Is that what the spaceship will experience? No, no. B, as measured by observers on the spaceship. What's this asking me to find? T0. Penella, my green sheet, is there an equation that has a T0 in it? Yep. Is the T0 by itself in that equation? Nope. What's the square root doing to the T0? Adding, subtracting, multiplying, or dividing? It says T0 minus. It's dividing, so how do I move the square root over then? What's the opposite of dividing? Timesing, right? We'll get this. T0 equals T. Instead of writing the square root, can I just put that little gamma abbrev there? Because it's sure handy. So it's going to be 16.4. I'm going to use my answer button. Times the square root of 1 minus 0.95 c over c all squared. Ethan, do you see? Do you see? Do you see? What do you see? And so I'm going to try typing this in one line. So I'm going to go answer button times square root bracket 1 minus 0.95 squared, because I want to see how accurate I can be. And I get 5.127472. I'll call it 5.13, but I'll leave this on my calculator. Now, if you didn't use your answer button, if you use 16.4 or 16.42, you'll be off a tiny bit with what I have. Almost done. So it'll take, as far as we're concerned, 16.4 years. They'll arrive, let's say if we started in the year 2000, well, 2020 is a nice number to do math with. If we launch them this year, they'll arrive for our 2036, but they'll arrive for their 2025. Okay? How far away is this star? 15.6 light years away? No. Only relative to us. Question? No. They're, relative to them, time is still moving normally. Okay? C. Suppose the spaceship trailed out a cosmic tape measure behind it. What distance would the spaceship measure to get there? Well, here's what I'd like you to do, if you don't mind. Put a little C there. Draw a line down the middle of your page. The way that we did this last time is we went D equals VT, but we said it's going to be V time on board. And we went D equals 0.95 C, that's the speed, times, I'm going to write 5.13, but I'm going to use my answer button. So if I go 0.95 times answer button, I get 4.871098. I'll go 4.871. 4.871, and that's light years because there's an A next to the 5.13 because it's light years. Now, we did that last class, and we said that's a little strange that they measure a different distance. I know you're looking at the clock. Patience. Here's why that's occurring. Instead of finding the distance, let's treat it like a length, where L0 was the original length of 15.6 light years. V is 0.95 c. Let's find the relativistic length. Basically, you can imagine their trip like a giant meter stick. And you can imagine the spaceship isn't moving. Space-time itself is moving backwards relative to them. We'll just pretend they're at rest and the universe is moving. That means the universe is going to be seen by them to be shorter than a regular meter stick. How much shorter? Well, L equals L0 times the gamma function. Is that the right equation? I'm going from memory.
Yes.
So it's going to be 15.6 times the square root of 1 minus 0.95 c over c all squared. Do you see? Do you see? Do you see? What do you see? So if I go 15.6 square root of 1 minus 0.95 squared, I get exactly bang on the same answer as before. And what we've really just done, Deegan, is we've proved that the length contraction equation is a valid Einsteinian equation. I didn't derive it with you, but the fact that we were able to get the same answer using the time dilation, which I did derive, this is correct. So the reason they're experiencing a shorter length is because, as far as they're concerned, they're not moving. Space-time is moving backwards relative to them, and since it's moving, it has to get shorter. Again, what that means is it's impossible for us to measure distances in the universe. We always are implying relative to what? Well, the Earth at rest. But as soon as we travel that distance, we'll get a different answer. I'll take your question at the end, because here's where it gets weirder, but cooler. So what does this mean for an object that travels at the speed of light, like a photon? Let's take this length equation and let's put in the speed of light. So instead of a v on the top, put a c there. Owen, what's c divided by c in your head, please? What's anything divided by itself? What's 1 squared? What's 1 minus 1? What's the square root of 0? So remember the light from those far-off stars that I was talking about? Not only do they not experience time, they don't travel the distance between the star and the Earth, because distance doesn't exist for them. They left the star, they arrived at the Earth, they didn't travel the distance in between because distance is non-existent. Once again, for those of you on YouTube, I've turned on the flash on my phone. Do you see the photons? As far as those photons are concerned, they've existed since the beginning of the Big Bang, and they're seeing the end of the universe simultaneously. But because distance is non-existent for them, they're experiencing everywhere in the universe right now, too. Because distance doesn't mean anything to them. They're everywhere and every when at the same time. Have I mentioned that light is special? Because it is. Mr. Dweck, how do I travel backwards in time? We'll finish with this. Put your pencils down.